Inference for population proportions. In this program, we'll learn how to use the one sample z procedure to make inference for a single population proportion. Note that this is exactly the same z-test for proportion that we learned to run in Unit 2. We'll also demonstrate use of the chi-square test of independence to determine whether an independent variable has a significant effect on a dependent variable. Of course, because this program is on inference for proportions, all of the data that we're using for these tests have to be in categories. Even if we were to begin with a quantitative variable, such as amount charged or such as household size, again, we would need to group those variables, those quantitative data, into categories in order to use these techniques. So let's look at an example that uses the one sample z procedure for making inference about a single population proportion. Test to determine if the population proportion of BAs differs significantly from 50%. So here we could see that we would like to make an inference or a statistical guess about a single population proportion. That's what the question is asking. For this, we need a single categorical variable, at least in our sample data. Here we need only education level. We next need to calculate p hat, the sample proportion of BAs, which is simply the number of BAs divided by our sample size. The z-test is only going to compare p hat to the assumed population proportion of 50% or 0.5 to determine whether there is a statistically significant difference. To run our z-test for this single population proportion, we could use our Excel tool, Inference for Proportions. We simply need to specify the variable number 5, which is education level. Our success category, which will determine p hat, is BA. On the worksheet tab z-test for proportion, we need now to formulate the null and alternative hypotheses. We're comparing p hat statistically to an assumed population proportion of 50%, and we'd like to know the probability that a random sample of 109 will have a p hat value of 60.55% when the population has a true proportion of only 50%. And we could see from the two-tailed p-value that this p hat is rather rare if, in fact, the true population proportion were 50%. So we clearly can reject that null hypothesis. Our test statistic is a simple z-test statistic. It tells us that p hat is 2.203 standard errors or standard deviations of p hat above 0.5. Clearly enough for statistical significance at the 5% level. Our confidence interval can help us offer a revised estimate of the true proportion of BAs. At 95% confidence, I would estimate somewhere from 51% to 69.7% of the population of cardholders will be BAs. And we could see clearly that the interval range excludes the test value of 50%. Every statistical test has required assumptions, or at least requirements for safe use. Even our simple one sample z for proportion has such a requirement. Proportion is binomial, so we could use a binomial calculator to see if our p hat, in this case, would likely follow an approximately normal distribution. If we input a sample size of 109, that's the size of our sample, we'd like to see the binomial distribution if we assume a value for p equal to 0.6055. That's our p hat. And we could see quite clearly that in this case, when n is 109, and when our estimate of p is 0.6055, this binomial would, in fact, follow an approximately normal distribution, very close. Remember our rule of thumb: if both n times p and n times 1 minus p are at least 5, or by a stricter standard, some would say by at least 10, we could assume that p hat follows a normal distribution and safely use the z-test. The one sample z is fine if we're needing only to make inference about a single population proportion. But what if we'd like to test the effect that a categorical independent variable has on a categorical dependent variable? For example, test to see if gender has a significant effect on the amount charged. We've already run this test using our two-sample t. Gender was used as a grouping variable, and then we compared the means statistically, the mean amount charged for both men and women. If we group those amount charged data into categories, we could look at this effect of gender differently using the chi-square test of independence. Remember always, for any of these techniques, our data are in categories. Whether or not they begin quantitative, by the time they make it to our crosstab and our chi-square test, they must be grouped into categories. Again, to run our chi-square test, we could use the Excel tool, Inference for proportion. Now we can recognize by the problem that in order to consider the proportion difference in spending category between men and women, as soon as we decide that we are going to group our dependent variable into categories, we know this has to be a test of proportion difference because both our independent and dependent variable are in categories and not quantitative. So the chi-square test is what we need in order to consider the effect of gender on spending category. And here's our three spending categories. First, looking at the cross-tabulation, and specifically at the conditional distribution of spending category by gender, we could see there are some notable proportion differences. These would be the type of differences that contribute largely to a significant chi-square result. On the worksheet tab chi-square, we could see that this is clearly a highly significant effect. Gender does have an effect on the likelihood of spending in a particular category. We would say that chi-square for 2 degrees of freedom is a rather strong 22.85. So we strongly reject the null hypothesis of no association, and we conclude that there is a significant effect of gender on the spending category low, mid, or high. But it's the post hoc analysis that's going to show us these specific effects. If we reject the null, we only know that there is some association. But it's either by use of the crosstab or the conditional distribution table or the clustered bar graph that we make a determination about specific effects. So here we could see quite clearly that if a cardholder is a woman, she is much more likely to spend in the high category than if the cardholder is a man. On the other hand, If a cardholder is a man, he is much more likely to spend in the low category than if the cardholder were a woman. Let's look at another example of chi-square testing. We'd like to test to determine if household size has a significant effect on amount charged, but we would like to use a chi-square test. With two quantitative variables, both would need to be grouped into categories in order to use chi-square. Quantitative data is very flexible. As we know, we could use simple linear regression to look at the relationship between household size and amount charged, because they're both quantitative. If we group only our independent variable household size into two categories, we could use that form of the variable for a two-sample t. Or as we have previously, grouping into three household size categories allows us to use that form of household size as an independent variable for our one-way ANOVA. Here we're regrouping both the independent and dependent variable into three categories, and we're going to look first at our 3x3 crosstab between household size, category, and amount charged category. So to run our chi-square test, we have on our Excel tool Inference for Proportion the household size data, which are quantitative, grouped into three categories. Low is 1 or 2 in the house, mid 3 or 4, and the high category is a household size over 4. And of course our amount charged data have already been grouped into our three categories, low, mid, and high. So that's not going to change as our dependent variable. We simply need to input the household size category, which is variable 2, as our independent variable. Now we could look at our crosstab and our chi-square results. Our crosstab shows when we run this test 3x3, 3 row categories and 3 column categories, we get 9 cell counts. However, to use chi-square testing safely, we want no more than 20% zeros. Here we have 1/3 zeros. The result can still be statistically significant. And in fact, household size category may have a significant effect on spending category. But this result, though highly significant and possibly a true effect, cannot be used and reported with confidence because we have too many zeros on our crosstab. So what can we do to produce a more reliable chi-square result? Here we would need to at least regroup the household sizes into fewer categories, because that would likely eliminate at least one of the zeros from our crosstab. We may need to regroup both the household size and the amount charged in order to run this safely as a chi-square test. To take care of the regrouping, I've returned to the Unit 1 Excel tool, Descriptive Statistics. Here is where I have the original household size data in its true quantitative form, and it's variable number 2. So to group these into only two categories, I'm first going to select all of the data, including the variable names. Then under Data, I'm going to select Sort, and I'm going to sort the data by household size, from smallest to largest. Now, very simply, I'm going to rename every data value that's a 1, a 2, or a 3 low. And everything else will be high. And the way I do that in Excel is simply by typing low and dragging it down. Everything else will now be the high category, and we just need to drag it down. Now, before copying over our household size data onto the Inference for Proportions tool, it's very important that I resort the data by the amount charged. If I didn't do that, and I copied in my new household size data, I would mix up the card holders, and that would make it hard for me to get good results. So now I have resorted by the amount charged, and I can simply copy and onto my data sheet, paste. So now we could rerun our chi-square test using, instead of the 3 categories of household size, only 2, low and high. So let's see if we've fixed our problem. And we have. We see that we do have 1 0 remaining, but that's 1 out of 6, which is less than 20%. It appears that the effect is still going to be significant, and it clearly is, with the strongest effects being, again, in the low and high categories, but not much of an effect in the mid category. So now this chi-square result could be used and reported safely. This concludes the program Inference for Proportion, One Sample Z, and chi-square test of independence.